Okay, so we're just going to do a quick video. I apologize. The copy on this was not super good. It's a little grainy, but should get the idea across. So these will be the answers for section A1 of the Oxford Physics book. So number one, we got a boat traveling due east for 2.5 kilometers, then travels due north for a further 3.8 kilometers. Calculate the distance traveled by the boat, the magnitude of the displacement of the boat, and the bearing from north of the displacement of the boat. So I urge you to look back. I actually posted these on Canvas. Hopefully this is picking up. The vector intro, this is posted. So remember what vectors are. They are essentially a quantity that has a magnitude and a direction associated with it. This also goes through how to add vectors. And just remember, if you have two vectors like A and B, then um, you add them by adding them head to tail. So if you have A and B, if you add A, this is A plus B right here. So A would be there, head to tail, and then the resultant is the green vector there. Also the same as B plus A. So it doesn't matter which way you do that. And then there are some sample problems in here that you could look at as well. Okay, so that would be a great thing to review. But for now, let's just look at our boat. Boat travels 2.5 kilometers to the east and then 3.8 kilometers north. I apologize. I had to change my frame of reference because I already had done the drawing. So distance is how far the boat actually traveled. Displacement is how far is it from the start point to the end point. Okay, so there's going to be two different numbers. So distance is just going to be adding everything up. You actually went 6.3 kilometers. Displacement would be 2.5 to the east and 3.8 to the north. When you add those up using the Pythagorean theorem, you get 4.5 kilometers, and that would be essentially northeast. Now, to find the bearing, you have to go into your trig and say, all right, I got 3.8 down, 2.5 across. So here is theta, and that's going to be the bearing from north, because that's what they asked for. And that's my frame of reference here. So theta is going to be tangent to -1, because remember, this would be tangent. Tangent would be opposite over adjacent. So 2.5 over 3.8, just take the inverse tangent of that, and you get 33 degrees east of north. For number two, the minute hand of a wall clock is 15 centimeters long. Calculate to the nearest centimeter the distance traveled by the tip of the minute hand and the magnitude of its displacement. So just to refresh, circumference is 2 pi r. So to find the arc length of anything, you just need whatever theta is times the radius, because 2 pi is the theta for an entire circle going around. So in this case, we are going from 12 for part A, it's 12 o'clock to 12:15. So 12 o'clock to 12:15 is going to be pi over 2. So the arc length is just going to be pi over 2 times 15 centimeters, which would be 23.6 centimeters or 24 if you round that. The displacement would be from the start point to the finish point. So it's going to be a 45-degree angle. We've got a 15 centimeter radius here and a 15 centimeter radius there. I'm just going to add, this is going to sound weird, 15 plus 15, but 15 to the right plus 15 down is going to be 21.2 centimeters, and it's going to be at a 45-degree angle. That would be the displacement, because that, again, measures from start point to finish point, direct line. For number two, it says 12 o'clock to 12:30. So that angle is going to be pi. So the distance will just be the theta times the radius. Pi times 15, 47.2 or 47 centimeters. The displacement very easy on this one because you go from the start point to the finish point. So 15 plus 15 is equal to 30 centimeters straight down. For number three, let me turn my page here. So for number three, this is dealing with speed and velocity. You have Ada and Matt start from the same point and ride in opposite directions along a straight road, each at a constant speed. After 1 minute, they are 580 meters apart. Ada is riding at 20 kilometers an hour. Determine the speed at which Matt rides. So here's Ada, there's Matt. They're riding in opposite directions, 20 kilometers an hour. Please get used to doing this. Convert everything to meters per second. It's just going to make your life easier. It's rare that they give accelerations in kilometers and hours. So if you just constantly go back to base units of meters and seconds for speeds, accelerations, distances, it's going to make your life much easier. So I did the conversion. 20 kilometers an hour is going to be 5.56 meters per second. and 1 minute is 60 seconds. So I just use distance equals velocity times time. I think in the book they presented it velocity is equal to distance over time, but this is just that equation rearranged. So 5.56 times 60 is 333 meters in 1 minute. So that means that Ada, who the one her speed was given, so she covered 333 meters in that 1 minute that they rode. Now, if they're 580 meters apart at 1 minute, then we can figure out the distance Matt rode by just subtracting. So 580 minus 333, we get 247 meters in 1 minute. So I just took 247 divided by 60 is 4.12 meters per second. I think that's the answer. I mean, they did not say a unit, but I did convert it to kilometers per hour by just using the exact same method over here. And in this case, it's going to be 3,600 over 1,000. So it's 14.8 kilometers per hour is how fast Matt is riding. Number 4, speed of light in a vacuum is 3 times 10 to the 8th. Sirius, the brightest star, is approximately 5.5 times 10 to the 5th. That's astronomical units from Earth. And so an astronomical unit is by definition the distance from the Earth to the sun. And 1 AU is 1.5 times 10 to the 11th meters. So calculate the distance to Sirius in light years. And light year is a distance because it's how far light travels in 1 year. So what I did was I figured that out first. Speed of light is 3 times 10 to the 8th meters per second. That is something you will have memorized by hopefully the end of your junior year. And so just take the speed of light times time, and that'll be the distance that light travels in 1 year. So 1 year, how much time is that? You could say 3 times 10 to the 8th meter years per second, but that doesn't really make any sense because you have a time unit in the top and a time unit in the bottom. So convert years to seconds. 365 days is 1 year, 24 hours is 1 day, 3,600 seconds is 1 hour. And then your seconds are going to cancel out. It's just going to leave you with a distance unit. So a light year is 9.46 times 10 to the 15th meters. So 5.5 times 10 to the 5th AUs is essentially, why did I convert that? Oh, because I needed to turn that into meters. So 1.5 times 10 to the 11th, they gave us that. And that gives us 8.25 times 10 to the 16th meters. So how long would it take? You just take the 8.25 times 10 to the 16th meters and divide it by 9.46 times 10 to the 15th meters, and you find it's 8.72 light years away. And I just did it as a conversion. 1 light year is 9.46 times 10 to the 15th meters. Again, sorry, the copy is just not that good on this. So number 5, we're talking about how a displacement or a distance versus time graph, the slope is going to give you the speed of the object. Okay, so slope of it, and I should say displacement here, not distance. So distance versus time would be speed. Displacement versus time is going to be velocity. And that'll come up in a second because of how I did the next problem on the next page. But if you can see this, the distance is here and time is on this axis. I recreated the graph that they had on there. So it says the speed in kilometers per hour of the train between stations A and B. So all I need is the slope. So it goes 1,000 meters. So A to B, this distance is 1,000 meters, and it took 80 seconds. So that's 12.5 meters per second, but I need to convert it to kilometers per hour. So again, there's that 3,600 over 1,000 or 1,000 over 3,600, depending on which way you are going. Okay, so it'd be 45 kilometers per hour. For B, the distance between stations B and C, so you just got to read the graph. And here's station B. So this is still station B because it's stopped, and that's at 1,000. Then when you go to C, it's at 1,800. Let me check and make sure. Yes. So it's 800 meters or 0.8 kilometers. And then finally, the speed of the train between stations B and C. So in this case, you just got to figure out what the slope is. So it goes from 100 to 160. So that's our time. And we know the distance is 800 meters. So it must be going 13.33 meters per second. Again, doing the conversion. And I get 48 kilometers per hour. And please note, whenever you see a unit in the denominator, IB will always represent it with a -1. That just means that it's kilometers per hour. My pencil got better for number 6. So Louise kicks a ball towards a wall that's 4 meters away from her. The ball moves at a constant speed of 10 meters per second when traveling towards the wall. The ball returns to Louise 0.9 seconds after it was kicked. The time taken for the ball to reach the wall. So velocity is distance over time. Rearranging this, just get time is equal to distance over velocity. So 4.0 over 10, and you get 0.4 seconds. And then it says the speed of the ball after it bounces off the wall, assuming that it is constant. All right, so the ball had to lose some energy in the collision. All right. It takes 0.5 seconds to return to her foot, because it took 0.4 seconds to get to the wall, and it took a total of 0.9 seconds for it to get back to Louise. So it must have been 0.5 seconds from the wall back. So I just put, now I did -4 because it's now moving in the opposite direction. I don't think the book did it that way, because they said the speed, and that's why. They said speed as opposed to velocity. So my apologies for that. It doesn't change the magnitude of the answer. It just changes the sign. And this is where it comes into play. Is for number 6, I have a completely different answer than what they have in the book. Sketch a graph to show how the distance traveled by the ball varies with time. I did a displacement versus time graph because I'm just so used to doing that. If you're doing a distance versus time graph, you would have a slope of 10, and then the distance would continue to go up. It would just be at a lower slope of 8. The displacement versus time graph looks like this, because if the ball started at Louise's foot and then ended at Louise's foot, the distance between the start point and the end point is 0. So the displacement graph should end up at 0, which it does for mine. For the book answer, they just have this continuing on, and they have a slope that's a little bit lower. So the slope is 10 to start with, because that was the initial speed of the ball, and they said it was constant. And then the slope for me was -8 on the way back, because it was moving in the opposite direction. However, in the book, they had it as positive. And I did want to show the actual. So I did a where it collides with the wall. There is an acceleration there. And so this displacement or distance time graph would both have a curved portion in here as it changes directions and changes speeds. So just thought I'd point that out. For number 7, we're looking at speed, or sorry, still distance versus time graph. In this case, they wanted, it's an ice hockey puck is hit and slides across ice. Distance time graph of the puck is shown. Estimate the initial speed of the puck. So in that case, you just got to try to find that initial slope. And I think I was pretty far off. I think they wanted something even smaller. But I said I did a time of 0.5, which was a single box. And the distance I got is 2.4, but it might actually be closer to 1, 2, 3, 4. So there's 5. So it's 1.2. Yeah, I'm not sure how they got their answer in the book, but this is not that far off. I think they said 6, but I thought it was more like a 5. Anyway, just take a reading off the graph. As long as you show that you took a reading off the graph, you would get points for that. And then the speed of the puck at 5 seconds, you have to draw what's called a tangent line. And on that tangent line, I just drew a tangent line there, and then I just did a rise over run. And so if you do that, you get 9.6 is my rise. My run is 5 seconds. So 9.6 over 5 is about 1.9 meters per second. And that was a pretty solid estimate for that right there. And then finally, the puck stops after 12.5 seconds. Calculate the average speed of the puck during the motion. So at 12.5 seconds, they say it stopped. So the total distance it traveled was 24 meters. So the total time moving was 12.5, distance was 24. So our average, essentially, speed was 1.9 meters per second. And finally, number 8, Stephen runs half a lap on a circular track of radius 25 meters. And he does that in 19 seconds. Calculate his average speed. So this goes back to problem number 2. You have figure out what the total distance he ran. So pi times the radius. Pi because he did half a lap instead of a full lap. So 3.14 times 25, and that gives you 78.5 meters. 78.5 meters over 19 is 4.1 meters per second. But his velocity is clearly not that much because he went from here to here. So his displacement was 50 meters, and he did that in 19 seconds, which is 2.63 meters per second. All right, I hope this was helpful for you, and I will see you all in August.